I'm very happy to have Van Wu here today to talk to us about kind of new things in perturbation theory.
Thank you very much. It's my pleasure to be here. It's been quite a while. I talk about some of the recent works that we have been doing the last few years with my student, Chen from Yale. So it's the new way we look at matrix perturbation, but let me give the setting first. So it's very standardized. We have a symmetric matrix with the spectral decomposition, where we order the eigenvalues decreasingly. That is, I use a phrase from data science as the graph truth matrix. And E is the noise, which it's another symmetric matrix, which can be either random or deterministic. The sum of these two is what we call the noisy observation. So usually that's the data we get from real life. And it has the corresponding spectral decomposition. So the perturbation theory is a classical one, and the goal here is just to bound the difference between the noisy observation and the graph truth with respect to some functional, which I call G, and that is some spectral parameter that you are interested in. So you can think about G as the largest eigenvalue, or the leading eigenvector, or the orthogonal projection onto the leading eigenspace, or the best rank approximation of A. So all these things contain information about the matrix, the graph truth, and people use them a lot in practice. So we compute them all the time. And there are bounds that we use not only in numerical analysis, but almost everywhere in very many areas of mathematics. So the first one is a Weyl inequality, which say that if I want to see the perturbation of the first eigenvalue or the second eigenvalue, then you just look at you have the trivial bound by the norm or the intensity of the noise right here. But this norm is a spectral norm of the matrix. Recently, people in statistics and data science use a lot of application of Davis Kahan theorem when you bound the perturbation of the eigenvector or the eigenspace. So here, phi of P is a orthogonal projection on the eigenspace spanned by the leading P eigenvectors. So you take U1 and U2, you look at that plane, the orthogonal projection of that plane. That is pi 2. And the bound is the constant time, the intensity of the norm, intensity of the noise divided by the gap between the eigenvalue that matter. So if you look at P equal to 2, you have to look at the gap between lambda 2 and lambda 3. And I will tell you why the gap appears. So, but the common pattern here is that most of the bound we have seen use the absolute strength of the noise.
Are we thinking of like the ground truth as normalized with a spectrum between -1 and -1, or no?
The eigenvectors are normalized, yes. We have like one here. They are unique vectors.
What is the absolute strength of the matrix? There's something new in matrices. Which norm do you use?
The spectral norm. So it's the largest singular value of the matrix.
Just a norm. Operator norm.
Operator norm, yeah. I mean, people, they use different.
There is a much better. There is a Hoffman-Wieland inequality, which is much better than Weyl.
Yes, it is like the total. Yeah, so today I will talk about this one more, but there is a general method that applies for many other functional. So here's a, for instance, this bow are sharp, and here's an example, very simple one. I take this, diagonal matrix E. The two leading eigenvalues are 1 and 1 minus epsilon, and the rest are just 1/2. I perturb them by the noise E, which have, operator norm, also order epsilon, is 2 epsilon to be exact, right? And I have the minus 2 epsilon at the top, the 2 epsilon in the second row. And after we add, we change the top to 1 minus 2 epsilon and the bottom to 1 plus epsilon. Right? So this one, in this one, lambda 1 is 1 and U1 is the 1, 0, 0, 0 vector. And the strength of the noise is 2 epsilon. In the second one, the noisy observation, lambda 1 tilde changed a little bit. It changed by epsilon. So it says that Weyl is sharp. And U1 actually changed quite a bit, turn into the second basis vector, it's the 0, 1, because the second eigenvalue take over with the first one. So it explains why you need to care about the gap between these eigenvalues, because the small gap actually guarantees that you can change the matrix a lot by a small noise. The bow are sharp, but we also, it is barely sharp in the sense that this noise acts adversarially to us, right? It hit exactly the two eigenvector, it matters. If we put this 2 epsilon thing in a random position, then actually it will not do anything. Yeah. So, and there's a lot of people who try to improve this bow in under circumstances like adding condition to the both matrix A and E. There's a very nice book by Bhatia that have a lot of perturbation bow up to 10 years ago. There's a few recent progress. And so the leading idea that we consider here is we look at not the absolute strength of E, namely the operator norm, but at the relative strength of it. So yeah, like the operator norm, but with respect to the ground truth matrix A. So one natural quantity to look at is actually the max of this bilinear form. I take an eigenvector of A to the left and an eigenvector of A to the right, and consider this. So it's clearly at most E is at most the operator norm of E. But if E doesn't act, doesn't act adversarially on A, then actually this thing is usually much smaller. If you think of E as a random matrix, right? And actually this is way smaller than the spectral norm of E by usually something more than a square root of the dimension. Yeah, so we go with the relative norm E with respect to A. A final definition is actually, we will see in the detailed calculation that you don't need to look at all the eigenvectors, you only look at those which are relevant to the problem. Like before, we look at the first and the second eigenvector of A. And actually, we may have to look at the third and the fourth and the fifth, but it's no reason to look at the last eigenvector. We can skip a few. So, and then usually in application that reduce the computation by another factor. So the general setting we look at is this. We consider a special matrix function of the following form. I fix a complex function f, and I fix a subset of index sets. Say before the subset was 1, 2, but you can also do things like 3, 4, 5. We look at the spectral decomposition and we define this. So basically what you do is you have the spectral decomposition of A, which like this. So it's the eigenvector to the left, eigenvector to the right. Yeah, so and now I take a function f in. Yeah, we f out all the diagonal here. And with the subset S, actually I zoom in only a subset. So yeah, so the final picture is like this. We have this f, after out, in S, and we still use the same.
And use zero or the remaining diagonal.
Yeah, the remaining as well. So basically, this is yeah, this is how people usually go just f of A, right? We functionalize f and then we project it onto a subspace spanned by an index set that we select. Yeah, for f equal to 1, we talk about orthogonal projection. So everything here is 1. So we just U times U transpose, but with restriction to certain row and column. So that's orthogonal projection onto subspaces. F equal to Z is another thing that we use very often in analyzing spectral algorithms. Is that actually it just the spectral norm, but the spectral decomposition. But we restrict to a subset S. So if we restrict to the subset which correspond to the largest singular value, we talk about the best low rank function rank of a given rank. And if you change f to be like the quadratic function or exponential function, then you can look at the low rank approximation of any matrix function, etc. So the method that we are using extend to any f, but in this talk we will focus on f equal to 1, which is already have a lot of application. So f equal to 1, then here we have the Davis-Kahan bound that I repeat. So we look at this orthogonal projection. We have to look at the gap because the gap was important, and the bound we say that the perturbation is less than the constant time norm of E divided by delta T. So we at least, well, the right-hand side have to be almost 1, right, to make sense. So we need a trivial bound assumption that the gap have to be at least as big as the operator norm of the noise. Usually in practice, we need much more. If we want to bound this thing by epsilon, then we need the gap to be huge. It have to be like 1 over epsilon times the spectral norm, which not always holds. Yeah, so a lot of Davis-Kahan bound application have to use this kind of assumption, which is sometimes too generous. So here's we have a few new bound. So yeah, let me state a few toy theorems just to give you the feeling about this kind of new theorem. First of all, we consider the case when A have low rank, so the rank of A is some parameter R, which is much less than n. You can think of R is the constant or maybe log n or something. And now all we need is, so before we will need something like this to make the a practical Davis-Kahan use. We need this very strong gap assumption. But now we only need delta P to be almost 4E. And the bar will become this. It will not be, basically we have the bar like the spectral norm of E divided by delta P. This is the Davis-Kahan bound. And the main thing we can do is that we replace that spectral norm E over there by X.
X was this norm that is relative to the ground.
Yeah, that's a relative norm. Yeah, so the x, that is this x we define.
You maximize over the eigenvectors of the ground truth compared to the error.
And it's a bilinear form, it's a both side. And then you have to adjust it by some parameter depending on R. Now there is a second term which still has the spectral norm of the noise in it. But now you don't divide it by the gap, you divide by the signal itself. You divide it by the lambda p itself. So the picture is like this. Yeah, so we don't really need, yeah, this guy can be small. Yeah, what we need is that actually the value of lambda p itself have to be big. And that one you cannot avoid because just think about it. You can think about it in two ways as an engineer, right? If the intensity of the noise is stronger than the signal itself, it has to destroy the signal. You can think about it as a random matrix people. There's a phenomenon called BBP phenomenon that say that if the intensity of the noise is bigger than the signal, timer right constant, and actually the whole matrix take over the behavior of the random matrix. It forget this information it carries. You look at a eigenvalue of a matrix like that, and actually the eigenvector look like a random vector. It has no correlation with the original one. So it was proved by Benarus, Blake, and Pesce maybe 10 years ago.
And you hope the dependence on R to be linear or sublinear?
Yeah, so in this one, the dependent is R squared, but we have improved version when the dependent is square root R, which I believe is right. Yeah, but that's the right question.
So when R basically approaches N, it matches the bound Davis-Kahan would give if E were a random matrix?
We are, so this is a toy example of a low rank case. So yeah, I will give you the real version when you will see that R can be N, but it almost never be N. It will be N and the matrix, the ground truth itself is so bad that doesn't make sense to talk about the projection anymore. You will see that. So yeah, typically R will be very small. See, unless they really want to screw it. Yeah, so still not the low rank case. Now, yeah, so now we try to actually even remove this assumption because it's still a strong assumption. It says that the gap have to be as big as 4 times the intensity of the noise. What about if the noise is square root N, then I still want this guy to be square root N. Okay, so yeah, so still the same thing. Assume that this higher rank R and lambda P is, yeah, so we want the projection on the leading P eigenvectors, and P is some small parameter, and lambda P is bigger than 0. Yeah, so there's now 2 parameters I look at. The X I had before, which also measure the interaction of E with the ground truth matrix. Another one which with also measures what?
With the noise matrix.
Yeah, E is a noise, but the UI are the eigenvector of the original of A. Yeah. The other parameter we also have to look at is that we take the image of E with any eigenvector and multiply with another image. So we look at O vector like this, and we take the inner product with another one. So I and J here is important that they are different. So
it's not the same with each word. I'm missing something. It's not the same using in X each word.
Yeah, here you have E squared.
Yeah.
E squared.
So E squared with different vectors, or
yeah, or E with
same.
Yeah, right. And in the E square, one you normalize by 1 over lambda P. So that makes them of the same order of magnitude.
So in the binary forms in X, there is cancellation, but in Y, there is no cancellation because you squared E.
I square E, but E square is still quite random. So
What kind of what's the
The eigenvalues become
intuition?
positive.
What's the
intuition,
difference between
okay.
X and Y, like what?
Okay, so you will see it in the proof, but at least in the random case, right? Let's take something like GOE, the random matrix with Gaussian variable. So this guy is, we know that is about 2 times square root A. Now you take the inner product of this with, you take the product of this with any fixed vector. This thing is still no order square root n. There's no cancellation here. A random direction spin expand by square root n. Now, but this one you multiply with a fixed vector on the left. You are gaining because this v is here, and e of u here can be very long, but it is have a random direction, right? So it's almost orthogonal to this v. So if this guy is a Gaussian vector, then it's more or less orthogonal. So here you actually solve order 1, maybe with a log. And then you save square root n. The same thing for EUI and EUJ, right? Take the inner product of this. Both of them are long, order square root n, but they are almost orthogonal. So this guy is actually of order square root n, not order square root n squared.
Oh, I cannot equal J. So
Yeah, that's why I directly have to write down. Yeah. Otherwise, you square it.
that's okay.
So
Is it accurate to kind of say that when y is small, you have this like specific basis of orthogonal vectors of like of A, and you want E to kind of shift it to stay orthogonal?
yeah, so yeah, it measures the interaction of E with the eigenvector of A. Yeah, so if they are not adversarial, then we are gaining.
But the difference is that in X, you're measuring the perturbation of X with respect to kind of the all spaces. So in
No,
Y,
I don't measure the perturbation of X. I use X as a parameter to measure the perturbation of the eigenspace.
right.
I don't measure the perturbation of X. Does it answer the question?
No, my question is, can I imagine that when y is small, this is saying that the matrix E is like moving this basis of, well, or not basis, but these orthogonal vectors to things that are also kind of approximately orthogonal to one another?
Yeah. So if they don't correlate with the eigenvector of A in the adversarial way, and you can measure that, then you are winning. And there are cases when it is easy to compute. Yes.
For analysis purposes, or just to follow it, can't we assume that A is diagonal without loss of generality?
No.
No.
Because actually my E is even deterministic, so you can.
It is deterministic.
So yeah, the theorem we have is the deterministic one. And even for random one, you can only rotate with Gaussian matrices. But if you have other kind of randomness, you can rotate. Yeah, so the assumption here we have to make instead of the Davis-Kahan assumption is this. Yeah, we still need this operator normal E to be small, but now small compared to lambda P, not to the gap, right? That's what I said before. We need X to be small compared to lambda to the gap, but X is a reduced, strength, the reduced intensity, so it's usually much smaller than the norm of E, as we illustrate in the random case. And the third one is slightly, harder to imagine, but it say that E square have to be small compared to the signal time the gap. It's still better than the original Kahan. Now, if we have this tree, then the bound is something like this. We have the leading term is X over delta P. So replacing X, the norm of E by X. The second one is what I had before, right? So we have the norm of E have to divide it by the signal. And the third one is Y divided by delta P. But this one is usually very small because Y itself is even less. If you see the definition here, we have n, square root n, right? But now we divide it by the signal itself and we assume that the signal is big already. So this is even more silly than the second term.
Excuse me, I have a question. You go back.
Sure.
I'm just looking at that third term there.
Oh, this one.
Yeah, I mean, delta P is less than lambda P, right? So.
Yeah.
Isn't that worse than the first term? Isn't that strictly larger? Because also R is.
No, yes, worse than the first term. It is something like the.
Okay, it's like somewhere in the middle between.
Right. It is better than the original. It is Kahan, but
It's still worse than the other. Okay.
Sometimes delta P can be bigger because if lambda P plus 1 is negative something, then yeah, then it can be the same order of magnitude.
Okay, sure.
All right, so what the bound is this, all right? The P is that it replace E by X, and you have the second term, which is necessary because of the phenomenon that I talk about in random matrix theory. And the third one, we also have example to show that it can be a dominant one and be the truth. So all the three terms are sharp up to the 12 actually. Yeah, so in the case the rank of the graph truth is order 1, then it just simplify to this, and we compare this with the original Davis Kahan things. So it is
So what the first and third term.
have lambda, yeah, divided by.
They differ only in the theorem. Just differ, you say X plus Y. I don't know why you separated.
Oh, because only this I can only do when R equal to bigger or 1. Oh, also, they have the same square root
The
PR.
same square root PR divided by
Right.
delta P. So,
Yes.
yeah, I don't know why they were separated. It's times X plus Y.
Yeah, it's X plus Y. And it is two different parameters to measure the interaction with the eigenvectors of A. Yeah, so I say that the example with the random noise very easy to see that how much we save, right? So it is random, namely that it have independent entries. Let's say that they are sub-Gaussian, which means 0, and bounded variance. They don't have IID bounded variance. Then this guy is order square root n, x is order 1, and y is order square root n divided by lambda p. If lambda p is forced to be bigger than square root n, then that's y is even smaller than x. Yeah, so here, we put everything together with the basically order 1 divided by 1 over delta p plus 1 over lambda p with respect to the original square root n over.
So lambda p can be negative, right?
Yeah, in this case, I assume it's positive, but it can be negative. And all right. Yeah, so here's a general case that explain what I say by we only need to define x with respect to certain set of eigenvectors. Yeah, and now the general case, assume the matrix have full rank, the ground truth matrix, they have full rank. The parameter R is not the rank of the matrix anymore, but something like this. I set the set distance, lambda bar, and the set distance means that if I go from lambda p that far away, then I don't have to worry about the perturbation anymore. So let's say that we have this picture. Yeah, we care about the perturbation with respect to this subspace defined by the eigenvectors of the first p eigenvalues And we go far enough so that we make sure that the perturbation of the eigenvector, which is of index, at least r+1, is not going to do anything with this. Yeah, then that is what I call a safe distance. And if you go that far and you see only r indices here, and that is my r. So it doesn't have to be the rank of the matrix. It's more like the effective rank with respect to this very particular problem, because the rest doesn't matter. Right? And usually this R is small, at least you have a big cluster of eigenvalue near, near the place that you care about, then you are in trouble. And you will be in trouble because you have a lot of guys in here who have the tendency to swap, right? So the example I showed before with the diagonal matrices is that when the eigenvalue gets swapped, the eigenvector gets swapped, and then that causes a lot of perturbation. Yeah, so if you have a huge number of guys here, they all have the potential to jump in, and then you are in trouble. But you don't have too many, then you are fine.
Is this leading you to a definition of the number, like this effective rank thing, or?
Yeah, that's, well, not exactly effective rank in the traditional sense, but effective rank with respect to this problem. Yeah, like the rest of the matrix, we can more or less forget. Yeah, and if you have certain decent decay on the spectrum, then usually R is small. Usually I take this guy to be about lambda p over 2, so I just have to go half distance. So let's say that you go from lambda p to lambda p over 2, how many eigenvalues are in between? And if there are a few, then we are okay. And then we define the x and y a little bit different. So x is still the same, but with the new parameter r. And y, we have to take into account that the distribution of the eigenvalue as well. Before all this, lambda L is equal to 0. It should be r over here. Before everything is 0, but now I just have to take the actual value in. Yeah, so the new bound, the general bound is the same, just with the lambda bar replacing the lambda p as before, right? So everything is the same. I take lambda bar to be whatever the bound I want to achieve. Let's say that I want to bound everything by epsilon, then I just take lambda bar to be e times epsilon to the inverse, and then I compute the rest. Yeah, so this bound is sharp up to constant factor with respect to both the assumption and the bound. So we can argue that we need all this assumption, all the three terms in the assumption, and we have construction showing that each of the term in the bound, each of the term here can be the dominating one and representing the truth. So, and easy to extend to Hermitian matrices instead of symmetric, rectangular matrices, and you use singular vector instead of eigenvector. You can do any general index set instead of the first, P indices. You can do any other subset. You can generalize it to any function f, as we discussed here. Now that part needs a little bit more work. And we can also do perturbation bound for the eigenvalues, not only the eigenvectors or, some matrix parameter. Yeah, so there's a lot of application we can do here. What is good for us is in many applications are small by definition, and in real life, a lot of data set also have very small rank. So A has a low rank or approximately low rank, or in the worst case, it have a spectrum which decay reasonably faster. So the effective rank is small. That parameter R doesn't cause too much trouble. And yeah, actually RV asked about the R. Yeah, so the R actually is the square root of R. And I think, yeah, that's about the truth. And in practice, also, if the noise E is often random, although our theorem is for deterministic, either it's random as the white noise, or it is defined from the content of the problem. And I will give you a few example how to see that how E is defined to be random. And there are a lot of them situations like that. Matrix completion, the hidden partition problem, like hidden click, or people in statistical with SMB problem, stochastic matrix block.
You mean SBM?
Oh, SBM, sorry. The Gaussian mixture problem, right? You have sample and you have random noise that give you a matrix when E is Gaussian and A have rank equal the number of the center, the random specification, which is actually basically the matrix completion problem, but another way around, or the covariance problem, computing the covariance of a random vector. So here, for instance, let me go through the matrix completion problem that you can see how E is defined, the noise is defined. So matrix completion is this. We have a big matrix, which we can only observe a fraction, like 10% or 5% of it. And the goal is to recover this matrix from what you observe. So it gets very famous through the public challenge called Netflix challenge, maybe about 15 years ago. A lot of money and 1,000 teams competing for it. So Netflix, the matrix here is a rating. You have millions of viewers and tens of thousands of movies. Now, of course, this can only be done if we have assumption. If the matrix is arbitrary, then there's nothing we can do. So the assumption people made, which now becomes standardized, is that A has low rank. The observed entries are selected randomly, so you don't have any pattern in the observation. And this one is the top one is incoherence. Assumption that basically say that the eigenvectors are delocalized. So that means that the matrix doesn't have too much information on the single. They want to avoid this case. The matrix have only single non-zero entry, right? Then you never observe it. But that single and everything else is zero. So this situation is caused by having the eigenvector very localized at the coordinate 1. So people do this. Now, but to put it in our framework, let us assume that every entry is observed with some probability rho, and we set the unobserved entry to be 0. Right? So you either see the original data or you see 0. Then the observed matrix is a random matrix because, because of the assumption, and the expectation of that is exactly rho times A, right? Because you specify it by a factor of rho. That means if I scale it back up by rho, by the reciprocal of rho, then I have a random matrix whose expectation is exactly A. It's unbiased observation of A. Then I can write A tilde here as A plus E, right? Exactly the model we are considering when E have independent entries, which means 0. And this is good enough to apply the parameter X and Y with the saving. We don't need Gaussian noise to obtain the saving. We can obtain the saving under much weaker assumption of the randomness. Yeah, so for this, there are many approaches to this. So the original paper of Candace and Tao use convex optimization. So you get the data, which is the very sparse matrix. You optimize some, you try to fill it as a target of the convex optimization problem. This have polynomial running time, but it's n to the 4th or something. It's not very fast in practice. And then people try to do spectral algorithm to make it fast. So there are many approaches, but the typical one is one by Kasheva, non-ternary, and O. They just compute the rank R approximation of the input So assume that they know R, which is a big assumption. But then we have something that they can show that it approximates the original matrix in Frobenius norm. And then they use that as the base to do gradient descent to refine. And they say that sooner or later you will get to the real matrix with some speed. They don't really analyze the speed, but yeah, believe that they did go there. And what they need is they need to know R, and they also need the condition number to be small. It's the ratio between the largest and smallest singular value of A. So here we can do a different algorithm that we still take this A tilde as an input, and I compute some rank P approximation of A tilde for a properly chosen P. I don't need to know R. I just look at the spectral map of A tilde, and I say that, okay, this P is good enough for me. Say P is 25, and I compute that AP. And then we can prove that this approximate A, the original matrix in the infinity norm, namely every entry is approximated within epsilon. That's the best you can do. If the entry is in the, irrational, you cannot compute it exactly anyway. So the best thing you can do is approximate it.
Is P supposed to be order 1 here? I mean,
What?
the number of observability should depend on P, right?
Yeah.
So is P order 1 in your bound?
No.
I'm a bit confused. If your rank P, well, R is the rank of the matrix.
Yeah.
So then you should need to see at least n times R entries to have a.
Right. There's some hidden parameter. That
Okay.
Yeah. But you are right. If the case when P is a constant, like 1/10, then you have this kind of bound. Yeah, there are other things you can do. For instance, one of the very trivial application we can think of is with protecting privacy. So usually people have data, like again, when the rows are indexed by individuals and the columns are their information, and you want to compute some global, signal out of it, global information out of it, but without revealing the information of the people, right? And the standard way to do it is to add noise to the system. So you just add a huge Gaussian noise to every entry, and then you protect the information of individuals. On the other hand, when you compute it with a noisy matrix, then you make some error on what you want to compute. And that is. And one of the things you want to compute is the low rank approximation, and Vishnoi and Mangobi have some paper on that, and we can improve that very easily. I mean, the original paper is like 80 pages from JACM, which is not a trivial one, but this proof is only like 2-3 pages. We can do covariance with spikes. I show you the proof actually in the next 5 minutes. Yeah, we can do covariance with spikes. So there's a model in statistics. They have to compute the covariance of a hidden distribution, and the hidden. We assume people assume that the hidden distribution have spiked, and then we can do it very efficiently. We can do perturbation of eigenvalues, although it doesn't fit into this picture, but there's a way to do that as well. So there are a few other things that we can do.
What does that mean, perturbation of eigenvalues?
Yeah, like the Weyl you can improve with the X and Y. Yeah, so let me spend the last 15 minutes talking about the method, which we call the combinatorial contour expansion, which is extension of the contour method, which is sort of classical in perturbation theory, but not so well known otherwise. Yeah, so we start with the Cauchy integral theorem. If we have a simple contour and f is say a nice function, then yes, so this contour is like this, and the point A is inside or outside the contour, that will determine the value of the integration. So we interpolate with respect to this contour. Yeah, so people use that to do contour analysis on matrices. So if we have, the kind of matrix functional that I define here. So we,
Just a second, what's the license?
wow.
Can you go back one slide?
Oh, sure.
Just to see the license side. Okay, yeah.
Yeah, so we define, the key thing is that we have the denominator z minus a, and that is going to the, to determine that where a is. Right, so we can do this and put it into the framework of this. And yeah, so if we start with this FPA, which we single out the spectral decomposition of FA, but only we truncate it up to index P, right? So when F equal to 1, we actually have the projection onto the leading eigenspace. F equal to Z itself, we have the low rank approximation, so on and so forth. Then that is equal to this. So that's the first key, because I use the gamma to
A of P, huh?
Yeah.
right. Which one?
The right-hand side, there's no P.
A of P.
Right hand side here?
Yeah.
Oh, because I use the gamma single out all the P, right? The gamma is contained lambda 1 and up to lambda B inside. So because of the integration theorem, that's zero out everything outside. So I don't need to. Yeah, so I use the shape of gamma to do the projection. Right, and we do the same pattern for the noisy one. Right, and now we come to the, well, I cheat a little bit here because the same gamma doesn't have to contain the first P eigenvalue of the noisy one, but let's assume that for a moment.
I'm sorry, but this equation 8 is very new to me. So what's going on? How do you plug in the Cauchy contour formula into this matrix thing?
I just do the Cauchy formula for the middle part of this picture. Right. So, yeah, I do the Cauchy here. Right? I forget about the left and the right eigenvector. I do only the Cauchy here, so I integrate it coordinate-wise.
Okay, but what is this Zi minus A inverse?
Oh, because that is a F over Z minus A, right?
Yeah.
And so Z minus A here is actually Z minus lambda I. It's well, people in random matrix theory call it the resolvent. Yeah, but that is the Cauchy theorem in action. Yeah, so assume for a moment that the same pattern holds for this guy, for the tilde guy, namely that they have the right eigenvalue in this gamma too. Not always, but for a moment that assume that it does. Then you have the contour inter-identity for the perturbation, which is this. Just take two integral, subtract each other out. Right, and there's again from random matrix theory, you have this resolvent formula. Oh, actually, this used in any different area of analysis too. It's not only random matrix theory, but that's where I learned it from. But yeah, so, and very easy to check it by in dimension 1. So you have to really fit in higher dimension. And if you, so basically you have to handle this guy, right? And you do this, and you do it repeatedly, then you would have a series like this. Right. Yeah, because in this one, you do it for one step, you have this one. You turn the difference into a product. Right? But the product still have the tilde in it. You don't want the tilde in it. Right? So you split out the A part of it, and you repeat the formula for the tilde minus the original. And then you keep repeating, then you have this series, right? Everybody agree? So this is also a standardized step. Yeah, and also we have a sum like this, and the difference is a sum of this fs from 1 to infinity. And you can use some sort of triangle inequality here. So yeah, so the key point is to bound this fs, right? So the fs is have these are rather complicated looking formula in itself. It have this thing repeated x times. So e times z minus a, my inverse again e time, and we do that a lot of times. Yeah, so for the original, this Kahan, you can do, well, this from the Cato's book in functional numerical analysis. So you can do it in a very trivial way. Namely, you just bound the integration by absolute value of the inside. And that gives you exactly this. And you can see the term of norm of E divided by delta P from here, because you want to bound the norm of this. And you balance out with the norm of E from the outside. In each of these, you have E repeated S time. So you have E to the S from the outside, and this one contribute 1 over delta. So yeah, and then if for the case when f equal to 1, you get back the Davis-Kahan bound. It's actually one of the proof of the Davis-Kahan of the original one, but the later. Now, recently, there are people who make final analysis on this. They actually compute the first term exactly, F1 exactly, and then they bound the higher order term in very similar manner. So actually, in the higher order term, we will have E divided by delta P, but now square, because you start from the second term. So actually, they improved bound from E over the gap by E over the gap square. So a quadratic improvement plus the first term that they can compute exactly. So that there's quite a few literature on that too.
So delta S is delta P here?
Oh, yeah, delta P. Okay. Yeah, I just say that you can work with any contour or any subset S. Right, so one of the, in the early stage of the study, maybe 3 years ago, we observed that some very simple thing you can do is to do bootstrapping, because, well, I mean, it suggests itself because the nature of the thing is fractal, right? You repeat itself, but you do the resolvent formula again and again. So why not bootstrap, right? So the bootstrap just work like this. You put the integration, the absolute value inside the integration again, right? And you take out the first term. But from the second S equal to 2, you can split out the part which is equal to the original one, S equal to 1, multiplied by the extra E time Z minus A inverse, right? Because every single time you repeat, you have an extra E by the resultant formula, you have extra E time E to the minus A inverse. Now, if we assume what I show you once, that the gap is at least 4 times this guy, then this term is less than 1/2. And actually, you will have what you want to estimate on the left and the right. You have 1/2 of exactly that, plus the first term that you split out to start. And you can compute the first term exactly. So, yeah, so you have this and this. The thing is that this thing is very easy to generalize for any f, because you don't have anything to do with f. You just take the maximum of f as at this term. That's how we improve the analysis of Mangobi and Vishnoi for the privacy protecting. Yes, so that is only that. Yeah.
So under this gap condition, I guess that problem is also easy to resolve, right? Like the fact that lambda I tildes also need to be inside your contour.
Yeah.
So in this gap condition, I guess that's trivial.
Yeah. And so the big problem here is that it still need this strong gap condition and this suboptimal in R, as Avi said that, yeah, it should be square root R rather than R square. So what is really the combinatorial contour expansion is the next step that we do. That's, I think,
Always
to
somehow.
deny everything I said up to now. Right, so now we do things somewhat differently, right? So so the key thing to analyze is this inverse, right? Z minus A inverse. We write the spectral decomposition of this, and we split it into two parts, I and J. When I is a set of important indices that we define this way, we go from P and we go up to R. That those are the important one, which has something to do with the perturbation, and the rest is just, you know, junk you have to handle. Yeah, so we split these things with respect to P and Q. Yeah, right. That's the two terms. And now we expand this product out. So you will have 2 to the S plus 1 terms, right? So you write every P and Q out, which look rather terrible because even if S equal to 3, this already have 16 terms. So that's the second expansion. Now, there's two observations that helps a little bit. The first one is the only term, in every term we have PE here, the noise matrix interact with the matrix P, which consists of the important direction, the important eigenvector. So that is an interaction that we want to exploit, right? We want to make that interaction quantitatively into the formula. So if you see E times P, then we are getting. Now the only term which doesn't have any P in this is the OQ term. But if we look at the Q term and we expand this again now into each of the term in Q have n minus R elements in it, right? So Q is this big sum. Now I open this big sum in this formula. It will end up with n minus R to the S minus 1 term, so together. But each of them is of this form. Now the key in this is that any eigenvalue involving in this form are outside the contour. So when I integrate that one, I get 0. So the whole thing with the OQ is 0. I don't have to care about this term. And this term is a bad one for me because that doesn't involve the interaction of the noise matrix with the important eigenvector. And the other one, of course, they do not vanish, but there we can rely on this interaction to do our saving. And let me give you one example. When you see how it goes, the very beginning, when S equal to 1 and F equal to 1, 2, then you will have a term like P times E times P. So here P is a sum of this inverse over the good direction. And you expand this product, you have the sum over I1 and I2, you have product of 2 reciprocal, and you have the product of the E in the middle like this, right? Because you have P times E times P, so you will have a big matrix here, right? Yeah, but then you see that you can integrate out this guy with no problem. And this thing in the middle says in J. Now this is a matrix, right? You have E multiply a matrix of rank 1, another matrix of rank 1. But if you write this thing out, and actually you have this. So this is a matrix of rank 1 and norm 1, but this is our quantity X appear. So you see how X appear. So the rest is something like this. The main difficulty to do all this is that after the second and the third expansion, the formula become a very big sum, right? You have the PQ that's give you 2 to the S sum, and then each of them is n to the R term. So and each of them look like this. You have some function in Z times the series of vectors and matrices multiplied with themselves. the thing in Z look like this, and it have all kind of possible sub-indices, and HZ you cannot factor out because it changes from term to term. So it depends on the patterns of the indices. So, and the delicate thing is that you need to treat the complex part, namely the H part, with the linear part together. You cannot split them out and say that I bound this one by the maximum, that one by the maximum, and merge them together. Because there are some compensation when you add them together. And the third thing is that when we do the integration of this, there's many ways to do the integration. The one thing you want to use immediately is the residue theorem. That you have to, integrate such kind of thing, and but it's just not the right way. Yeah, so it cost me a year sitting on the residue theorem. That would lead to anything. It's just a formula too complicated to analyze. So what we do is to go back to combinatorics, that we desire a simple algorithm to execute the integration of the complex part. Now this algorithm gives us a combinatorial profile for the term in terms of a graph. So each term like that will go to a graph. And I use this graph to profiling the term, so I can collect the term with the same graph. And the term in the same graph, actually, together, we can estimate it by combination of analytic and linear algebra and combinatorial pool. And then it turns out that the term in F1 and F2 dominate, the first two F dominate, that give you the term of, the definition of X and Y, and the rest are negligible to the first combination of the contribution of the first two terms. And the first two terms we can compute more like exactly, and the rest is negligible. So actually the bound is sort of exact. There's nothing there to omit. Okay, so thank you.
Is there any intuition? Okay, you explained that there is combinatorial decomposition to graphs and collect. Is there any intuition why the terms beyond 1 and 2 disappear, don't affect the boundary?
We can go further, but it's not worth it. We can go to F3 and have maybe X, Y, and Z, right? But then the condition and the conclusion gets so complicated that it's useless.
So it can move to.
We can go to any order, but it's not worth it. Our life is short.
I have a related question. If I only wanted to prove the conclusion of your theorem for when E is a GOE matrix, is the proof simpler, much simpler?
I guess so. I mean, it can be diagonal matrix to start with, and then it helps a bit. Yeah, we never try that case. For GUE or GOE, a lot of things simplified,
right?
But I don't think it's simplified to that degree, because you still have to integrate this thing out somehow.
So you still do the contour integration. Like I see.
All right, thank you. Yeah.